I'm working at the Physics Research Center of the Hungarian Academy of Sciences, and there is also András Leitereg, my student, and Gábor Lehel is not yet here, but we are working with recursion schemes, and I would like to talk about, give a small introduction about this kind of approach, and András will talk about the details of our project, that is a GPU code generator that is powered by recursion schemes. Yesterday we already heard some stuff, but I would like to reiterate some part of it. So, a short introduction. We are a physics research institute. We are a member of many large international collaborations. You might have heard about the Large Hadron Collider, or the gravitational wave detectors, or the fusion experiments, or the Rosetta mission. These are always on the newspapers and the news. You can hear about them, and Wigner is contributing to all of them and many more collaborations. We have the Wigner data center. It is the largest off-site compute infrastructure. This is the Tier 0, the heart of CERN, that is placed at the institute to give a large amount of compute and storage power to the LHC data analysis. So we are really, at an institute level, we are supporting the research with IT solutions and things like that. But it also means that we encounter lots of codes used in physics, and it is really an insight how big collaborations handle all the coding stuff. There is a smaller group that I am part of, the Wigner GPU Lab, that is dedicated to parallel computing, to give support to the end users about how to code, what kind of hardware to buy, how these systems are working, and they can experiment with different vendors' cards. We both have Intel, AMD, and NVIDIA cards to play with. There is a small cluster, and the users can develop their codes on these systems and run smaller simulations or data analysis. We're organizing the GPU Day every year, where we invite speakers from companies and within Hungary and neighboring countries to give talk about various different fields, not just physics, but also biochemical applications or image processing, everything related to massive parallelism. And we have lectures in modern scientific programming series where we talk about different aspects of computing and programming to teach all the people who are interested. We are giving lectures at the University. Our main projects are usually centered around physics simulations or some analysis and visualization tools. We are mostly working with particle physics simulations and gravitational wave simulations. But most importantly, we always try to seek for new solutions, new technologies that could be adopted, because everything is progressing and it's changing very fast, and the new tools are always more capable than the previous ones, and if someone does not keep up with the advances, it is not productive. We are members of the OpenCL advisory panel and contributing to the new standards a little bit. So yeah, we are looking for tools. One reason for that most physics comes from really high-level abstract models. We have crazy equations, and we need to get down to hardware, because usually the problems that we need to solve are really computationally intensive. So, for example, at the LHC we have gigabytes of data coming out of the detector every second, and we need to process it online. For gravitational waves, we need to calculate thousands of templates, preferably on the fly. So when the data comes out from the detector, we need to immediately run lots of templates and search for similarities, so that the other visual observatories can turn their telescope in the right direction and look for the event. And these problems need really, state-of-the-art solutions. And functional programming is becoming one of the most important tools that we need to use. So we have a lot of structures that are mostly trees. We have hierarchies of every kind, and naturally it comes with recursion. So I would like to talk about these four subjects a little bit. So physics physics, and especially theoretical physics, starts from equations. So we really have quite a lot of different equations that are really, really complicated and cast into some extremely compact form. These are the Maxwell equations. That is lots of equations. If you write out, there's 4 equations, but for 3 vectors, so it is at least 12 equations that are compactified into this form. And this is just one of the simplest examples. So most people at our institute usually work with Mathematica, Wolfram's Mathematica, and crunch crazy equations. And at the end, they would like to see some numerical solution because, you know, analytics can get only so far. And we need to somehow map these equations down to the hardware to run it. But there are crazy number of assumptions in the background, so it is really a complicated task to get something, you know, get out a programming construct from these equations. So abstractly, the problem is that we start with some kind of equation, and we need to get down to, for example, GPU code that is running on the hardware. Okay. So the tool chain, if somehow, is this, that we have some symbolical mathematical expressions. And the first step is somehow, after some changes, to get some linear algebraic expressions, because this is another level that is, you know, that is a domain-specific language, and many tools are developed for this kind of level. And from that, we usually get down to some high-level programming constructs, something larger than C, for example, but at the very bottom, we always end up with something like C code to do the low-level programming. Just a few details about what to think about. So at the symbolic mathematical level, we have different kinds of symbolic transformations, differentiation, integration, series expansion, simplification, substitution. So this is something that the Wolfram Mathematica is unbeatable in, because it has a crazy number of heuristics and tables about how to simplify and substitute stuff. At the linear algebra level, we have a vast number of numerical solver choices that is usually coming from the equational structure. So once somehow you build a model and decide what kind of special case you would like to investigate, it somehow implies the numerical scheme that you can choose. So you remain with a fewer number of them to experiment with. It usually ends up with matrix tensor manipulations, linear manipulations, matrix decompositions, and things like that. It could be either dense, so it is a continuous block of memory, or some sparse representation, because there are really big areas of zeros inside these structures, and you don't want to store that. But of course, then you get a little bit complicated logic. At the high-level programming terms, we can think about types, higher-order functions, some fusion and fission identities, and the specialization of more generic algorithms. For example, those numerical solver templates somehow happens in this area. And at the lowest level, we would like to talk about memory layout, because it's very important for performance, and also temporaries, that we have automatically generated stuff of operations, and we need to minimize the number of temporaries and memory copies and things like that. And of course, we are talking about massive parallelism, and then the scheduling of the different threads comes into the picture, and you need to think about it also. So you can see that there are trees everywhere in this approach, because you have expression trees that represent the original mathematical equations or the program logic at some point. We have abstract syntax trees that come into the picture at the code generation and transformation level. We have nested generic algorithms, because you can imagine that it happens that you have some iterative numerical method that inside calls some linear algebra, and this method is embedded in another optimization code that is embedded in some even bigger algorithm, so you will end up with a nested series of algorithms. And yes, of course, we have data structures that are nested, because we have some space partitioning that leads again to trees and things like that, and the hardware is hierarchical also. I would like to bring some examples for that especially. So one aspect of this, that we have hierarchical parallelism. At the largest level, we have computing centers. In the right upper at the image, you can see the LHC computational grid, at least some part of the world shown that is densely connected, because there are a number of computing centers in Europe and in America and other parts of the world where there are computational centers with different size of clusters inside them, and they are connected with high bandwidth optical cables. And inside this computing center we have a vast number of racks where there are lots of CPUs and storage installed. Inside this you can encounter multiple devices. So up to, say, 10 years ago everything was CPUs, but after that the GPUs came into the picture and hybrid clusters started to develop. And the latest news is that even more and more clusters start to use FPGAs, field programmable gateway arrays, to have some special logic installed on them, because they're, for some tests, they are even faster than GPUs and CPUs. And inside these devices, you will have usually multiple execution units. So it is not in news that in CPUs we have multiple cores, and inside GPUs you have thousands of cores, and also in FPGAs you can build lots of cores. And each of these cores might run lots of threads, different number of threads. So we, at the very end, we need to really scale our problems inside this vast hierarchy. The other part is that not only the execution logic, but also the memory is hierarchy. So at the largest and most slowest part, we have some storage that is usually a disk or the dying out tape technology. Inside, or at the lower level, we have the device memory that is either the RAM inside your computer or the VRAM on the GPU or some installed RAM on your FPGA. This RAM is usually cached in some smaller parts but faster areas, and there are parts of this cache usually that is shared between the threads, or there is a special memory that could be shared between a certain number of threads. And all the threads are operating in a set of registers that are the fastest and slowest amount of storage memory available. So you need to somehow manage a structure like this, that you read some data from your disk or from a network or a file handler. You need to split it between different areas of your devices on the CPU or on the GPU. You need to manage the cache hierarchy, which parts, the most frequently accessed parts, should we keep in these cache areas, and you need to keep in mind the register and thread local memory usage and things like that. And it is not trivial, so it is really, you need to really think about how to split your problem in a good way. So I think I can convince you that there are lots of trees in this picture, and we need to deal with these trees somehow. So what are trees? Trees are structures that are made from the same repeating building blocks. We have some leaves and some branches and placed repeatedly on each other, and it is not a surprise that these are recursive structures, so recursion comes into the picture. And now I would like to show some really introductory examples to trees to illustrate a few algorithms, exactly the same ones that were yesterday, just more samples, more understanding. So let's start with a really simple tree in Haskell that really just includes some topology that is either the final empty node, or we have a binary branch containing the very same data type. Okay, and we need to, for example, have an algorithm that calculates the depth of the tree. If we are at the empty level, it is really a zero depth tree. If we have a branch, we are of course now one level higher, whatever it is below we need ourselves, and we need to calculate the maximum of the left and right sub-trees that are below us, and we can recursively call ourselves. And of course, if we have finite memory, we have a finite tree, and at some point we will hit all these empty parts and we are finished. So you can experiment, create one empty tree, a level 1 tree, or a level 2 tree, and you can call this depth function, and you are happy with that. What is the point that you need to see? That this is something called primitive recursion. You explicitly write out the same thing that is defined on the left-hand side to the right-hand side, and you need to do it every time you create a new recursive function. So there are some problems with this approach that, not really satisfying. You need to write each recursive function that you make for your specific data type, and your data type could be different for many cases, and you need to repeat your recursive function each time. You might be not just passing one simple result from a subsequent call to yourself, but pack it into some complicated structure, for example a tuple or even more complicated stuff, and you need to pack and unpack between the function calls, which is maybe not so, so it involves some boilerplate. And the same recursive logic might get implemented multiple times because it is hard to abstract it out in this way. So let's see a different approach, and this is called structured recursion. I am not going to explain the fixed point structure and the fixed point combinator. It was done a little bit yesterday, and last year I was talking about this in a little bit more depth. But we can define these three structures without explicitly mentioning the recursive part. We have a parametric position now, and it will be replaced later with the same structure when we call this fixed function on it, that will place repeatedly the structure in itself until this function reaches the empty leaf and the recursion ends. And now we can create one higher order function that is, so to say, primitively recursive, because we mentioned the same name on the right hand side. And this is the simplest one is the catamorphism, and I'm going to give an example for that. Here we write out the name itself. So it basically unpacks the structure, calls the fmap that maps the same function on the branches, or does nothing at the empty branch, and then calls, then on the result calls again this function that handles our logic on the tree. So the same example to calculate the depth of the tree. If we are at the empty level, we return 0. And when we call when we encounter a branch, we just calculate the max of the left and right. But now the branch is missing from the right hand side, because what this algorithm does is replace this parametric structure when returning with the sub results placed in these recursive positions. So we are not returning at this point a branch of trees, but we are returning with a branch of sub results. Okay, and now everything got a little bit simpler. And of course we are doing the same logic. Okay, so few reasons why it is better. This was discussed a little bit yesterday. Separation of the recursion logic from the data type. So we have now a different logic for what kind of traversal we would like to do, and we can define the data types in a different place, and everything is separated. Parameterization over the data type and the application logic, and somehow it is more clearly expresses intent. So you don't need to figure out from a primitive recursion what the hell it is doing, because if you see that it is a catamorphism, then you immediately can know what is going on. And you only need to know what is happening at each level in the tree, and it is at a much more separated place. Okay, so this kind of recursion scheme, the catamorphism, deconstructs a fixed point structure, a functor, into a summary value of type A, and you can see it from the signature that at the very end we will have a type of A. And the parameters that you need to supply is this deconstruction logic that will be applied at each level inside the tree itself, that fixed point structure, and you will get the summary value. Okay. And there is a category theoretical dual, anamorphism, that constructs the tree from a seed. You can see that everything is reversed with respect to the catamorphism. We now end with a logic that takes one value and creates a functor of a value from it. We start with a seed value and end up with a tree, because this functor will be fixed. And everything is reversed. I will give examples what it is useful for. For example, we need to create a tree that has a given depth. Okay, so I would like to have a complete tree of depth n. For example, if n is 0, I'm stuck with an empty tree. But if it is m, then I create a branch and decrement this value and put into the branch parts, and then I can repeatedly apply this to create the full tree. Yeah, it is a simple example. There is one more of these recursion schemes that I would like to introduce. It is the paramorphism. It is the generalization of the catamorphism. It makes the original structure before the evaluation, so the tree itself, to be available for this operation at the levels, and it is also the memory of the sub-results. So you can see here that now we have a tuple that contains the tree and the sub-results inside the tuple, inside this factorial structure, and we'll create a summary value out of this. And otherwise we're doing the very same thing. We take a tree and end up with a summary value. For example, this is useful when we would like to depend on what kind of branches have been inside the tree before we summarize them. For example, we need to count all these kind of half branches inside our tree. So when we have a branch, but one part of it is empty and the other is another branch, we need to calculate these, and we can do it as the following. At the empty node, of course, we end with 0. If there is there is a branch that is both empty in both of these sub parts, then of course it is not a half branch. If it is a full branch, so a branch that we have again 2 branches beneath, it is just adding the counters that they accumulated, and we only add 1 in the other 2 cases when inside the branch there is a branch and an empty node, or reverse, there is an empty and a branch with exactly these structures. Then we add 1 to the already accumulated value, and by applying this paramorphism we're really counting these kind of structures. Okay, so let me mention some use cases. So this is the logic that catamorphisms do. We have a sub-result and we can somehow combine them to a new result. This is a bottom-up traversal of the tree. So first we go down and unfreeze the structure until the recursion ends, and there we start to do some logic and accumulate the summary results and go up to the tree. This is usually it is a decomposition of structures level by level. But we can also change the expression structure if we change the summary value to a tree. Okay, so we can replace this A with another fixed point structure, and we can change from one tree structure to another. So it is useful for evaluation, kind of logic serialization. So you have a tree structure and you need to create some bit series from it. Calculating all these quantities bottom up. And the other important thing that is coming from theory, that we have a combination and combination identities. The combination says that if you have a tree transformation like catamorphism, that from a tree creates another tree, and there is another catamorphism that is a usual generic evaluation kind of catamorphism, you can fuse them into one traversal by composing the application logic. And there is another one that if you have 2 catamorphisms that operate on the very same tree, you can again do it in one traversal by splitting into a tuple the one-by-one applications of the logic at each level. Okay, the paramorphism does not only work with the sub-results, but you can depend on the branch type and create a new result. It is the same stuff, just like for the catamorphism, but you can access to this sub-result structure. At the very end, you have access basically the whole tree that you started with at the root level. You can access it if you wish. The anamorphism is something that is building a structure level by level. It is a top-down traversal of the trees, so we start at the root and go down to the leaves. This is deserialization, so like reading from a stream or a file or something like that. You can calculate all these quantities to the bottom or create a structure from the street. You can experiment with building such a good image where you start with the length of a branch and the angle of it and change just a little bit in each application of the function that you are applying in the tree, and you are always making 2 new branches and change the seed value a little bit. So you change the angle and the length of the branch, and you can go to some depth and create this fractalized structure. There were more examples in yesterday's talk. and also last year I gave some more about expression trees, and András will talk about even more. But the main question is, what is this height for? So we just gave a fancy name for some algorithm patterns and why it is good for. So it is not exactly the case. So it is something that is again coming from categories theory. It is important that we have a theoretical background for this, because it is giving us a little bit more than just abbreviations. And this is exactly these combination and fusion rules that are coming from theory with these constructs, so you can really automatically reason about how to simplify series of these recursion schemes and combinations of them or products of them to create and reduce the number of traversals that are needed. You can browse online for a collection of these recursion schemes that are meant to put together lots of them. So there is a series of more and more generic traversals. Now this is one for consuming a structure and the other one is creating a structure. I'm not going into the details. The interested readers can consult the references later. I just would like to mention, for example, two of them, that when you are doing an anamorphism and the catamorphism after each other, you can fuse it into one traversal, and it is called the hyomorphism. It could be used to build different kind of numerical quadrature rules that are evaluating numerical integrals, and you can really abstract over even the Monte Carlo stuff and the analytic, so to say, or predictable quadrature schemes inside just one recursion scheme. There is a mutuomorphism, that is a mutual recursive pair of functions calling each other in a lockstep. It could be used to create the adaptive solvers of numerical differential equation theory. So something that we gain with these approaches, that is just like in the imperative words, going from code to kind of programming to algorithms. So we are no longer working with primitive stuff that is really easy to mess up and make mistakes, but we now have restricted setup with well-known properties and well-known combination rules. It is really easier to see the patterns and solve much more complex problems with these tools. And I would like to give another example that is, say, fully out of functional programming world. But I think it is really interesting to take a look at this. Who knows neural networks? Okay, so everyone is an expert in this field also. So just a short summary. Neural networks come as the new hype train of the last years. This is because there is now cheap and high performance computing available, GPUs again. And there is another reason for this is the large annotated data sets that were accumulated during the last years. So it became feasible to feed quite lots of data, thousands of images, thousands of text stuff or speech, recorded audio files into these systems with the expected results. And these networks can be tuned, optimized to perform some kinds of tasks on these data sets. One particularly important case of them is the recurrent neural networks that are used in natural language processing, speech recognition, things like that. So when you are dealing with a time series of data and you would like to analyze it. So you can imagine these neural networks as functions in the mathematical sense, where you have sets of weights inside them, and these do some nonlinear transformation on their input. And you can optimize these to perform some kind of task. And when given a data set, time series, they start at a certain point, take some input, process it, jump to the next one, process it, jump to the next time series point, and so on and so on. So if we are really spelling out it in a graphical way, so here is a neural network. It has some state inside it, the weights. We supply some input one at time point 1, we get some output and change the internal state of the network. The very same network receives the input at time 2, creates another output, changes again the state, and this goes on until we would like to do. It turned out that some problems that have more hierarchical structure For example, when you're really interested in the grammar of a sentence or some more longer correlated structures inside the data sets that you would like to investigate, these recurrent nets are not the ideal tool for that. And then some clever people come to the conclusion that some recursive neural networks could do the tasks. So let's see how these stuff are working. We have now a certain number of inputs, and we have the very same network logic with the same weights cloned for each of these inputs. They create some output, and then some of the outputs are again fed into the very same networks with the very same weights. So it is really the same function that is operating inside all of these regions. You create some output and apply this up to some point, and you will get some final output. So again, I would like to emphasize that this is the very same network with the very same weights that is operating, and it can solve really well all these structure abstractions that we would like to teach to these systems. So they are outperforming in recognizing even logical connections inside sentences, or really parsing these structures. Just one example from the literature, here it is used to construct the meaning of a picture from smaller parts. So it recognizes that there are trees, there is something that looks like the windows of a building, it has a roof of a building, there is a small crowd at it, and it constructs what is going on the picture. Okay, and it really needs a structured abstraction of these things, not just, putting everything together in a flat way. Okay, so it is really the same operation applied at the time in the tree. Is this sound familiar? Of course, it is something like the catamorphism. So there is a blog post by Christopher Ola that contains a list of these mappings. So different functional programming constructs correspond to different kind of neural network structures that are well known in the literature, but of course these other community of never used functional programming. And in particular, recurrent neural networks are just folds and unfolds on lists. So this is a flat structure, and recursive nets are Kaplan anamorphisms. Anamorphisms can be taught about when you have a network that creates a structure. So you for example, give some flat input to that, and it creates a tree-like structure. For example, generating some sentence or description or things like that. Okay, so there are quite a lot of recursion schemes. I'm arguing that it is useful to know them because in many fields you can recognize them and now think in a higher level about what is going on, and it could be easier to solve problems. My sample codes are in this repo. I highly recommend reading these two papers, one about the earliest introduction, and there is a unifying about. So these recursion schemes are really making up a more and more abstract tree of structures. So the most abstract ones are really more general cases of the earlier ones. So catamorphism is just the simplest one. It is okay. The fold is the simplest one that you can imagine, and then you can go up on the tree. There are lots of good materials online, and here are a few references for the neural network stuff that I was talking about. Okay, so András will talk about the rest, and he will talk about the real-life usage of these recursion schemes and all the details about GPU computing.
So we have this tool called LambdaGen, which we are working on to make our playing with recursion schemes useful, or at least look useful. Dániel talked about these steps of going from a high-level mass expression to low-level programming terms, which every single physicist has to do if he wants to do some kind of simulation or something like that. And they are usually not really good at low-level programming, so that's why we decided to make them a tool. Right now we start from the linear algebra and produce a GPU code that they can run. It's very important that our goal is not to beat the highly optimized and specialized codes written by GPU specialists, but more to to offer a compromise between minimizing the development time and the runtime for scientists who are not programmers. So the main parts of our tool is an EDSL embedded in Haskell, in which the user can define the computation he wants to run. And then we have a set of analysis and transformations which work on the expression tree built from these primitives. And because it's an expression tree, then all the previous theory applies that Dániel talked about. After that, we have GPU code generation. We produce Compute CPP code because it supports C++11, and we have some automatic memory management implemented in C++, but I won't really talk about the last 2 points because it's out of scope here. So yesterday, if you remember, we saw an expression functor from constant addition and multiplication. This is just the same. We have a little more of these branches because we have more to express, but you can see the same screen. You can see some lambda calculus, application abstraction, and variable, and some higher order functions familiar from functional programming. But can we really express at least linear algebra with those? We think that we can. So this example is the scalar product of two vectors, which comes from multiplying element-wise and then reducing to the sum. In our embedded language, it looks like this. We have helper functions to avoid the fixing each time you see on the previous slides. But otherwise, it kind of looks like the expression tree it generates. One interesting part is that we store the lambdas in a curried form to make partial evaluation possible. So you are already familiar with this fixing stuff. Instead of that, we use Cofree to make it possible to put annotations on the nodes of the tree. So at each node, we have the branching and also another value that stores some information or a set of information specific to that node. Yeah. This is the recursion scheme library of advertisement. Of course, we wanted to use that because why would we want to implement all the recursion schemes by ourselves? In that, these recursive fixed points are generalized into a type family, which is quite simple for fix. So it just lets you move back from the fixed form to the original. And with that, you can define the recursion schemes like this. So you have the unfixed becomes this project which takes the fixed form to the unfixed, and yeah, catamorphism looks like that. And there are all those. You remember that table a few slides ago? All those are implemented in this library, ready to use. So the first kind of challenge we had to solve is that we have these analysis steps that take an expression tree annotated with some previous information and generate some kind of new information. And we will put that new information into the set of annotations. So this set is constantly changing. So the analysis cannot depend on the exact set of annotations. Instead, it has to abstract over them, but it may require the presence of some. So, for example, you cannot do this analysis without the previous type checking annotation or something like that. This abstraction is provided by the vinyl extensible record package. In that we can, so the record fields are represented with a type level list. So whenever you see this type level list constructor, then it means that we are extending the set of the annotations. We can constrain the presence of some annotation and even the presence of a subset, which is very handy. So we start from an expression tree built by the user, and we want to end up with C++ code that evaluates the expression. Between those, we have a set of transformations. Each one synthesizes some new information, and we put those as annotations. The first step is the type checking. It deduces the type of each node from the types of the children. For that, so you can see the type of the algebras, and this is the type of the new annotation. It's either the type of the node or a list of errors. So when we reduce a tree to a single value of this type, we either get the type of the full expression or the list of type mismatches we encountered. And this is the algebra we use for that. This R is the set of the extensible record from Berényi that represents the annotation set. So if you just run this algebra, we end up with a single type. So the catomorphism reduces the whole tree into the carrier type. And that's not really good if we want to make additional transformation steps. Instead of this, we want to place this new type information at each node. So the respective partial result we want to place next to the existing annotations. To do this bridge between these two solutions, we have this adapter algorithm which takes a reducing algebra that has only the new annotation as the carrier type, and produces more useful algebra that instead of reducing it to a new value, it places that value next to the existing annotations. The next step is deciding which of the higher order functions we want to run in parallel. You know that map, reduce, or zip can very easily be parallelized, but of course not all of them, because once we encounter a higher order function and we decide to parallelize it, anything under that is already run on several threads, so there is no, we shouldn't start new threads under a parallelized node. So this works like it finds the nearest higher order functions nearest to the root that aren't parallelized yet. This will be a co-algebra because and an anamorphism because we go from top to down, and we will have a seed value that shows whether we have parallelized anything over the current node. You can imagine this as having two states, yes or no, if this third is not really relevant now. And the annotation we want to place is how many threads we have by now and how many threads we want to start here, if any. And yeah, so in the signature of the coalgebra, you see that we start from a pair which consists of an existing tree and a seed value, and we want to end up with a tree annotated with just this new annotation. the number of threads we want to start. This also loses information, so we define this kind of algebra which just produces the new annotation, but we also have an adapter algorithm for this, which turns the algebra into one that makes annotations and appends the new annotation to the rest. The next step is allocating storage to all the partial results, because on a GPU you can't do dynamic memory allocation. You have to calculate the whole memory requirements, so how much memory each partial result needs. This algebra decides for each node whether that partial result needs new memory, or it can place its result in the memory of the parent node. After that's decided for each node, we collect the memory requirements. So the previous one was a top-down analysis, and the collection is a bottom-up. We end up with all the memory requirements. And in the last step, we generate GPU code. It's a really good use case for a catamorphism, except that we don't just need the code generated from the child nodes. We would also like to have the storage identifier of the child nodes, because we need to know where they placed their partial results. And with a catamorphism, you would only have the generated code for the children, so we had to use a paramorphism here to also access the annotations of the children. Once again, this is all recursion schemes: a catamorphism, anamorphism, and the last paramorphism. This system has been tested on multidimensional linear algebraic expressions like matrix products and tensor products. It does work on CPU with simple STD threads, and also on GPU with compute CPP. And you can see all the implementation on my GitHub repo. Our further plans are we have two main plans. One is the hierarchical parallelization. So we would like to utilize the hierarchical memory in the GPU, the local, the shared memory, and the global memory optimally. And we want to utilize the theory, the equalities with mapfold zip. We want to find optimizable parts like maps after each other which we can fuse, and so we need to match and replace parts of the tree. And we have yet to research whether this can be done with the recursion schemes or not. So we are working on this tool to help scientists automate this work to go from high-level math to GPU code, and yeah, we think that we are going in the right way. And if Dániel wants to conclude with anything else, no. Okay, then thank you for your attention.
Okay, yeah, questions? Yes, go on.
So have you implemented any optimization transformation, or is it just a mapping with the analysis and the...
We have one test optimization, which is a constant folding that finds operations with constant arguments and computes that. It's just a catamorphism, it's a very simple one.
Definitely my second question, what framework did you use to change the parts of the yeast?
Yeah, so we can reduce some subtrees with a catamorphism, but yeah, as I've put on the last slide, we are really interested in knowing whether we can make inside replacements in a tree with the recursion schemes.
Yeah.
I have like less related to the presentation question, but from practice. Let's say you want to, or you calculate value that depends on handling inputs. And again, very complicated formula. And now, once you calculate it, and then you learn that 3 inputs, points change, and you need to calculate once again the whole, let's say, tree. Do you have some ideas what would be the better approach to do or to optimize this? Because obviously you do not want to recalculate full, or you do not want to do full recalculation, so you want to do it in an optimal way. Have you had this kind of problem?
The question is how often this point is changing and how up it is in the workflow. So of course, if you add the new term to your equation, you need to recalculate everything. There is no way around. Of course, if you have a floating point value changing somewhere because it is something measured, you take it as a variable and specify in your model that it is a variable parameter, and you build your tree with this assumption, and then it is not a constant, it's a variable. So it is a, I don't think a separate, up to a really far point you can get with this approach by really specifying what level you expect the change, and you just run things that are down from that or prepare for this change. I think it is not quite often that you need, you have a so big expression that you don't want to recalculate every part, but you need to, and you need to cache the sub-results. I think it generally it should be possible, but it is not something that it is common in the betas that we see.
Okay. Any other questions? No? Okay, then thank you again.